So if we go back to Archimedes' principle and we think about an object that's completely submerged and then we release it, we found that if the buoyancy force is greater than the weight of the object, then the object floats to the top, and if the buoyancy force is less than the weight of the object, then it sinks to the bottom. By definition, the buoyancy force is equal to the weight of the fluid that's displaced. And so in both of these examples, the buoyant force weight is just mass times gravity. So this is the mass of the fluid times gravity. So if I want to know whether or not an object floats or sinks, I could ask what property of the object and the fluid can we compare to determine if the object will float. And what I realized from these expressions here is that if you hold an object and you completely submerge it in a fluid, that you're displacing the same volume of fluid as you have volume of object. And I have gravity on both sides of these equations, so I can actually cancel out gravity from both sides of the equation. So I'm displacing a certain amount of fluid, and if the mass of the fluid I displace is greater than the mass of the object, then the object will sink. And if the mass of the fluid that's displaced is less than the mass of the object, then, I hope I said that right, then it will, if the mass of the fluid is greater than the mass of the object floats. If the mass of the fluid is less than the mass of the object, then the object will sink. And so since I could divide both sides of this expression by volume, because when I displace the object in the fluid, the volume of the fluid displaced is the same as the volume of the object. What this means is the properties that we can compare to see if an object is going to float or sink is the density. So if the density of the fluid is greater than the density of the object, then that means the object is going to float. And if the density of the fluid is less than the density of the object, then the object is going to sink. Or another way to often say this is what we learned very early on in our education. If an object is less dense than the fluid, then it will float. And if an object is more dense than the fluid, then it will sink. But it's all based on Archimedes' principle and this idea that the buoyant force is equal to the weight of the fluid that's displaced. So we saw in the PhET simulation with the wooden block that when the wooden block was submerged and then released, it floated up to the top. And when it floated up to the top, what we found was that during floating, the buoyancy force was exactly equal to the weight of the object. And that's always going to be true with flotation. So a floating object displaces a weight of fluid that's exactly equal to its own weight. In other words, the buoyant force is equal to the weight of the object, but by definition, the buoyant force is equal to the weight of the fluid that's displaced. So an object that's floating has to displace the same amount of fluid, the same weight of fluid as its own weight. So the way to think about this is that if an object is floating, that means it's in equilibrium, right? It's not moving. And so according to Newton's second law, the net force has to be equal to 0, which means that the upward force from the buoyant force, here's the upward buoyant force, that has to equal the downward force of gravity or the weight of the object. So, sometimes we think about this in terms of if an object is more dense than the fluid, then it will sink, and if it's less dense, then it will float. And so we could ask the question then, how is it that large cargo ships that are built to displace a large cargo ships which are made out of steel, and steel is more dense than water, but yet that cargo ship can still float? And the answer to that is those ships are built so that they can displace a large amount of fluid, right? So there's a large amount of the ship that's below the surface, and it's built to have this curve to it so that it can displace enough fluid so that the the amount of the fluid that's displaced here, that weight of that fluid that's displaced is exactly equal to the weight of the ship. If I crumbled the ship all up into a ball or a block, right, I take all that steel and I combine it and I make it into a block, then the buoyancy force isn't as great, right? So the same weight here and here, but there is a smaller buoyant force because this block is not displacing as much. Okay, let's consider what happens when I change some of the properties of the fluid. So, okay, so let's start with the brick. So I have the brick and the block, and they both have the same volume again, so they're both 5 liters. So if I take the brick and I completely submerge it in the fluid, it displaces 5 liters of the fluid, and the buoyancy force is 49 newtons, and the weight is 98 newtons, and so it sinks. So what is going to happen if we change the material, the fluid? Okay, so the volume of the fluid that's displaced should be the same, right? So let's make this material, instead of water, let's make it more dense. Let's make it honey. And what do we expect to happen? Do we expect the buoyancy force on this object to change? So I'm going to make it honey. And the buoyancy force is now 69.7 newtons. So when it was water, right, I don't know if I can get it right at water again, the buoyancy force was 49 newtons. And when I make it honey, right, around there, or even much larger, right? Let's make it honey. When I increase the density of the fluid, the buoyancy force on the object increases. And so this should make sense. So if we think about it, honey is more dense than water, and that means that if you have an equal amount of honey as compared to water, and we do, right, because water, we've displaced 5 liters of water, and when we change it to honey, we've displaced 5 liters of honey. So the buoyancy force is equal to the weight of the fluid that's displaced. Honey is more dense, which means it's more compact. So if I have 5 liters of honey, it's going to weigh more than 5 liters of water. Therefore, since the buoyancy force is equal to the weight of the fluid that's displaced, the buoyancy force is going to be greater when the fluid has a larger density. In the same regard, we can make the density of the honey we can make it less than water. So we're back at close to water again. All right, there we're at water again. And if we change the fluid to gasoline, the buoyancy force on that becomes less. So now it's less than 49. And so for the same reasoning, gasoline is less dense than water. So that means that if we still have the same volume, right? Because the object has a volume of 5 liters, so I'm displacing 5 liters of water, and I'm displacing 5 liters of gasoline. So gasoline is less dense, which means that it takes up, it's less dense, right? So it has less mass in a given volume. So 5 liters of gasoline weighs less than 5 liters of water. And since the buoyancy force is equal to the weight of the fluid that's displaced, the buoyancy force is going to be less. So by changing, if you have an object that sinks and it displaces a very specific amount of the fluid, you can actually change the buoyancy force on the object by changing the fluid. And so fluids that are more dense will create a larger buoyancy force, and fluids that are less dense will create a smaller buoyancy force. All right, let's go through that same process as we look at an object that floats. So we looked specifically at an object that sinks. And now we're going to look at an object that floats. So I'm going to take my my block, and I have it in, oh, whoops, hold on, let's take it out of there. Let's put it in water to start with, because we like to start with water. So I'm going to place my block in water, and I look at this and I realize it's floating, so the buoyancy force is equal to the weight of the block, right? The weight of the block is 19.6, the buoyancy force is also 19.6. At this particular point, I realize that I am displacing 2 liters of water. I have to displace enough water to equal so that the weight of the fluid that's displaced is equal to the weight of the object. So 2 liters of water has a weight of 19.6 newtons, which is enough to equal out the weight of the object. All right, so now let's notice what happens when I change the substance to something that is more dense. So I'm going to make this honey, and the block is still floating. And what I notice about the block as it's still floating is that the buoyant force has not changed, because if an object is floating, the buoyancy force always has to equal the weight of the fluid that's displaced. And the buoyancy force has to equal the weight of the object. It's equal to the weight of the fluid displaced, but it also has to always equal the weight of the object. So what happened? Well, what happened is that the block is no longer floating as far down under the fluid. It's displacing less honey than it displaced water. So why is it displacing less honey? Honey is more dense. So if I want to get a weight of 19.6 newtons of honey, I don't need as much volume of honey because it's more dense. And so it requires less displacement of honey to create that same weight. In the same regard, if I were to go from water, so I'm displacing, I can't get it back to water, 2 liters here when it's at water. If I change this to gasoline, right, gasoline is less dense. It's still floating. So the buoyancy force is equal to the weight of the object. And so I have to have enough gasoline displaced so that the weight of the gasoline is 19.6. But gasoline is less dense than water. So it takes more gasoline volume to equal the same weight of water of 19.6. So I'm going to displace more fluid. It's going to sink lower. So, I mean, I could keep going with this, and eventually, right, I'm going to get to the point where the density of the fluid is so small that it's causing the wood to actually sink. So if I compare, the density of the wood is 0.4 kilograms per liter, and I have made the fluid 0.36, this block is now more dense than the fluid, and so it sinks. And if I change it and I put it back up, right, so that it's more dense, the fluid is more dense than the wooden block, then it will float again. So there's a difference between floating and sinking. In the case of an object that sinks, the buoyancy force on that object can change as you change the fluid, right? So as I change this to something that's more dense, the buoyancy force increases, and as it's less dense, it decreases, because you're always displacing the same volume. On the other hand, if you have a floating object, the buoyancy force will always be the same value. It doesn't change regardless of how you change the density of the fluid, but how much fluid is displaced will change in order to keep that weight or that buoyancy force equal to the weight of the object. So there is a difference between floating and sinking, and we have to consider that as we look at examples. Okay, let's see if we can apply what we just looked at in the PhET simulation. So I have 2 identical cargo ships that float, with one in seawater and one in freshwater. Seawater is more dense than freshwater. Which cargo ship experiences a greater buoyancy force? So they are identical cargo ships in every way. So they have the same mass and the same weight, and they are floating. And so both ships are going to experience the same buoyant force. And the reason for that is because they're identical, and if they have the same weight, the buoyancy force must equal the weight of the floating object. And so they have to experience the same buoyant force. So this is like the wooden block that was placed in the fluid, and as we changed the density of the fluid, the buoyancy force stayed the same. We have exactly the same question. It's two cargo ships, one in seawater and one in freshwater. We want to know which cargo ship in which situation displaces more water and thus floats lower in the water. And so in this particular case, we found from the PhET simulation with the wooden block that when we changed the fluid density, the wooden block did float at different levels. And so it turns out that the ship that's floating in fresh water will displace more water. And the reason for that is because they do have equal buoyant forces acting on them. The buoyancy force in seawater and in freshwater is exactly the same, and it has to equal the weight of the cargo ship. But since freshwater is less dense than seawater, more volume of freshwater is needed to equal the same amount mass-wise of seawater, right? So seawater is more dense. It doesn't require as much volume of seawater to equal the same mass of fresh water. So that means that the ship that's floating in freshwater will displace more fluid, and thus it will float lower in the water.